So in this lecture, we're going to talk about vectors. It should be a review of what you've done before, but there's no harm with doing a review. The hardest thing conceptually and also mathematically is the leap from 1 to 2, then 2 to 3 dimensions. Very easy to do all this stuff in 1 dimension, it's very easy to do in 2 dimensions, but we need different operations when we reach to 3 dimensions. Here's just the dry definition. A vector is an object that has a magnitude and a direction. Hence, that's why we always see this classic image of it as an arrow. Yeah. The length is a magnitude, a force, and a direction. We can write them in this very nice format: 3, 4, or -2 thing. But what we normally have is a little arrow over. It's very important to include the arrow to distinguish a vector from a scalar. Now, in general, you talk about or-dimensional, or n, yeah? N-dimensional n tuples. Or 2, or 2-dimensional space, 2 tuples, 2 dimensions. Now, the operations that are very simple and work in 1, 2, and 3 are summation, subtraction. Yeah? Even kind of scalar operations work. Magnitude and direction don't work in 1D because there's no direction, but there is magnitude. 2D, you have a magnitude and 1 direction. 3D, you have a magnitude and 2 directions. 4D, magnitude and 3 directions. As they get more and more complicated, the ones that we really care about, because they'll turn up again and again, is versions of dot product and cross product. It's important to distinguish between each of these. Dot product tells you about direction, it tells you about magnitude. Cross product gives you a new vector. If you can keep that in mind throughout, that's going to make life a lot easier. So, simple summation. In 1D, 3 plus 4 is 7. Yeah? In 2D, you have a vector u plus v. Vector u is 2, 3. Vector v is 5, 6. 2 plus 5, 7. 3 plus 6, and that should be 9. So you can't add something 2D and 1D together. You have to make sure the dimensions are the same. How would I do this? Where do I add the 3? Do I add it to both of them? Do I add it to none of them? Do I add it to only x, only y? You have to think about that. And of course, 3D with 3D. 3 plus 5 is 8. 5, 8. 4 and 6 is 10. And 5 and 7 is 12. So very straightforward. Summation is so easy. It comes directly from 1 dimensions. Subtraction is identical. Yeah. Now, the only thing that could go wrong with subtraction is you might forget that the minus counts for both. Yeah. So in 2 dimensions, the vector 2, 3, which we'd just call u, minus v, that's 2 minus 5 and 3 minus 6. Yeah. The minus goes across. Okay. And then in 3Ds, it's very straightforward. Exactly like before, you can't subtract a 1-dimensional vector from a 3-dimensional vector. N dimension is fine. And now we get to the crux of a vector. Why you don't really think about vector calculus in 1D is because you only have one of these. In 1 dimension, you only have magnitude. In 2 dimensions, you have magnitude and a direction. In 3 degrees, you have all, many directions. So mathematically, a vector in n dimensions, in Euclidean space, so that's normal space, is defined as a list of real numbers. But it can also be divided. So there are terms here. The polar coordinates is another way of referring to this, where you can refer to them as a length and a direction. So let's start with direction. In 2D, so in 1D, it's trivial. If you're given the number 3, what's the length of 3? 3 is 3. Yeah? Now, what's the length of minus 3? 3 as well. You just take the absolute value. Or you could go to all the trouble and say minus 3 squared. Yeah? And square root it. In 2 dimensions, we have 2 values. And what we just do is the distance. So we assume everything is in reference to 0, 0. Yeah. So we want to find the distance, the length of the vector from 0, 0. So that's why we go 3 squared plus 4 squared. But you should think of it almost like that's 3 minus 0 plus 4 minus 0. 3 minus 0 squared, 4 minus 0 squared. That would be pertinent later on. In 3 dimensions, it's the exact same formula. You just take each of the components, 1 squared plus 2 squared plus 2 squared, and all square root. The length of that is 3. Yeah. For any dimension, the magnitude is just one value. It's just a value. It's the amount of power put into it, the amount of force put into it, the direction of it. Now, the amount of power put in a direction. Now in 2D, we have this nice little graph that we always know is that in 2D, you have an angle theta. So you have your length, which is your magnitude, and you have your angle. And so to do your angle, you just go back to your old rule. So Sokotoa, silly old Harry called herring troll of America. All you're doing is you have something of height y, length x. And you just want to find the angle of the triangle. And you use the tan rule. So tan inverse y divided by x gives you the angle. And that's what the angle is. So you know your directionality. So that's easy enough in 2 dimensions. But in 3 dimensions, you need 2 angles. Okay? So the first one, theta, that's like in the 2-dimensional form. Exact same formula. But the phi, you have to do a bit more work. This is the thing that tells you about the z angle. Yeah? So what you have to do here is you find the length of z and divide it, the length of the vector v divided by the z part. So tan is just 2 divided by 1, tan inverse, and cos inverse 2 over 3. Yeah. So once again, it's very straightforward, but it's making that connection going, okay, why is it 2 angles in 3 dimensions? Well, think about it. If I was on a flat plane, all I need is 1 angle to rotate. But in 3D, you have an angle that goes this way and that way. Yeah. So that's why you have 2 angles. The closest to kind of a simple multiplication, it's called a scalar product, because all it does is it scales the vector, makes it smaller or larger. So all a scalar product is, you multiply a vector by a scalar being a number. So if you have the vector 3, 4, you multiply it by 10, both 3 and 4 are multiplied by 10. Three dimensions, x, y, z, multiplied by a scalar, not a vector, but a scalar, so 1 dimension. So this is where you can do 1 dimension, but you're multiplying by. And so by multiplying, you'll make a vector longer. If you multiply the numbers greater than 1, if it's less than 1, it makes it smaller. It scales the vector. You can also change the direction of the vector by multiplying by a minus sign. Now, one thing that people like to do is create a normal vector. The reason why people like normal vectors is the length is 1, and so it's comparable to everything else. It's just sometimes easier to think about simple normal vectors. So let's think about in 1D, something's length 3, you just divide it by 3, and therefore it's equals to 1. It's not that straightforward in 2 dimensions. What you have to do is divide by the length. So if you're given a vector 3, 4, you divide it by 5. Yeah? And you can double check this. So that's your answer. That's your normal vector. But you can check it. The length of a normal vector, that's what this is saying. The length of a normal vector should equal 1. If it doesn't, something's gone wrong with the normalization. Why you want to make something of length 1, it's easier. It means that the magnitude of something doesn't matter as much. You just can look at directions. 3 dimensions, the exact same rule. You give your vector, you get your length of your vector, and you divide each of them by that length. Easy as 1, 2, 3. So here, to check it, you create the length of it, you show it that the length is the same as 1, and therefore it is a normal vector. Sometimes it seems weird to do things like normal vectors, but a lot of the basis, like x, y, and z, are normally 1, 0, 0, 0, 1, 0, or 0, 0, 1 for z. ijk vectors. And people like to think of them like that. So it's sometimes nice to rewrite things as normal vectors. In the next lecture, I'm going to talk about the dot product, and then in the final lecture, I'll talk about the cross product. And then in the tutorials, you're going to work on solutions for each of these.